All right. I think it's time we can begin. Looks like we have almost a full house.
We haven't even begun to discuss voting yet.
So it's really a pleasure to introduce Rosanne Di Stefano today. She's coming all the way from office P...
227.
227. I should have memorized that by now, but it's just down the hall. So across the hall and down. That's right.
It's a long way.
You're right. That was not precise at all. But it's still a pleasure to introduce Rosanne today. And I had the opportunity this morning to talk to her about her academic background, because usually in these introductions you say, Rosanne got her PhD with this and that and this. But I've talked to Rosanne before about her background, and today I got the details, and I thought it was pretty fascinating, kind of inspiring trajectory that she's had, because she started out her research at Columbia University, where she did a master's in physics. And then after that, she decided to switch and do field theory. And so she went to Stony Brook University, where she got her PhD working in supersymmetry. And then, continuing in supersymmetry, she was a tenured faculty at the New York Institute of Technology for a while, until she decided she wanted to go into astronomy. And astronomy took her up to MIT, and eventually where she is now, working on a range of things, as many of you know: binaries, triples, gravitational lensing, sources of X-rays, supernovae. And today she's going to talk about a number of those things. Mass transfer within hierarchical triples. So, thanks, Rosanne.
Oh, thank you. Okay, well, we're going to be talking about a number of different things today, but there is a unifying theme, which is in all of these cases we'll be talking about hierarchical triples. And in these triples, we'll have an inner binary and an outer star. The outer star is contributing mass to the inner binary. So that is the unifying theme. Plan of the talk is I'll start by motivating why is it that we'd like to talk about this type of system. And then we'll move on into three specific different areas. At least I think we will. Let's see. Okay, well, we'll then talk about mass transfer from a giant to an inner binary that's composed of compact objects: neutron stars, black holes, white dwarfs. So these are possible progenitors of gravitational mergers and type 1a supernovae. And the question we'll ask is, under what circumstances does mass transfer from the third star do something significant to that inner binary? And then we'll go on and talk a little bit more about the theory of whether or not there's something special about mass transfer in these systems by considering an extension of the idea of the Roche lobe. And finally, I hope to have time to at least briefly touch on a new model for type 1a supernovae that emerges from these considerations. I'll begin by thanking my collaborators, several of whom are in the room. It's been a pleasure to work with you guys, and in many cases we're in the middle of projects that I think are very interesting. In fact, I especially want to thank Sophie Schroeder, who's leading a collaboration to actually study mass transfer in these types of systems. So let's see if we can get this to play. What you're looking at is, think of all the motion in the plane of the screen. This is the inner binary. It's an equal mass inner binary. The third star is contributing mass. You can see that not all of the mass goes toward the inner binary, but that there is a stream. And in this case, the separation between these two stars is large enough compared to this separation that it's very hard for a circumbinary disk to form. So what you're seeing is you're seeing each of the individual components of the inner binary interact with the accretion stream. So the question ultimately, this is beginning stages. You're looking at a 3D hydro simulation, a slice through that simulation.
What are your units for T?
T is in units of the dynamical time of the mass donor. So, and you'll see this film again. what are we interested in? Well, we're interested in the fact that the binary components can gain mass. We're also interested in the fact that as that inner binary interacts with mass coming from the third star, even if none of it accretes on these inner objects, the mass is going to be draining angular momentum from the inner binary. So the angular momentum of the inner binary changes, and the combination of mass change and angular momentum interchange can change the time to merger if you have two things that are going to merge under the influence of gravitational effects. A very interesting element here is that this mass infall can be detectable at a variety of wavelengths, and I'll focus here on the X-ray. But there are a wide range of detectable associated phenomena. For example, if a merger occurs during mass transfer or during a common envelope, there can be a very interesting electromagnetic signature, even though you have two black holes merging. So there are a lot of phenomena that provide tests of this because it makes so many predictions. And we're just in early stages of doing this. In fact, there have been very few papers, very little work on this topic of mass transfer within hierarchical triples from the outer star. So in general, we'll be interested in how the outer star changes the inner binary. So let's spend a moment or two talking about a famous binary, Algol, which was known to the ancients, including cataloged over 3,000 years ago. In almost every culture, it's considered some type of a really bad luck kind of star. It's called Demon's Head, the Ghoul's Head, Satan's Head. And maybe the reason is that although it's steady and bright, every 2.86 days, it kind of blinks and dims. In the late 18th century, Goodrich conjectured that there might be an object passing in front of Algol, and it was a century later, approximately, when our own Edward Pickering demonstrated that this is an eclipsing binary. Now, for modern-day astronomers, we know it in another way because we talk about the Algol paradox. Because in this system, there are two stars, one of which is more massive and should be younger than its companion. Well, it is, according to our estimates of its age at the present day, it is younger than its companion, although they should be at the same age. The companion is a slightly evolved star, and we know the solution to this paradox is that the slightly evolved star has been donating mass to Algol A. So we have Algol A, Algol B. It's a mass transfer system. And when you have mass transfer within a system, the stars influence each other in very significant ways. Algol B has turned Algol A into a more massive star, which will now have a shorter lifetime. If this were in a cluster, Algol A might appear to be younger than any of the other stars in the cluster, although they all formed at the same time. We might refer to it as a blue straggler. So the occurrence of mass transfer from one star to another leads to many, many interesting phenomena, and we have experts sprinkled through the audience on very many elements of these processes. So I'll simply mention, oops, not going backwards, but going forward. I'll simply mention that the phenomena include this Algol phenomenon that we just discussed, cataclysmic variables in which a white dwarf accretes from a low-mass companion, leading to variability on many timescales. Type 1a supernovae, which lead to ion enrichment of the interstellar medium, and a wide range of other things, including gravitational merger events, which lead to short gamma ray bursts if the things that are merging are neutron stars, and enhancements in our process elements. In fact, last week when Chuck Steidel was here, I had a conversation with him, and he said, I always tell my students that 80% of all the phenomena of interest to astronomers today are due to binaries. So the question that we want to answer today, well, we're not going to answer this question today. The question that we want to begin to address today is what happens if you have a third star? How does that change things? How does that contribute to the phenomena we could see? Well, I don't know how many of you knew this. I didn't know until very recently that algol is a triple. Okay? And not only is it a triple, it's not going to have the kind of dramatic interaction that we're going to talk about in another minute, but actually in the future, after these two have evolved and either merged or become two probably very likely helium-like dwarfs orbiting each other, this guy, at least through winds, will be able to donate mass to whatever remains at the site of the inner binary. So the fact that this one system is a triple may not prove anything, although it's suggestive that it happens to be one of our most famous, well-known stars. But actually, a variety of studies through the decades have shown that triples are common. There are a wonderful sequence of papers by Tokavinen. As part of Max Mo's thesis, we found that most young high-mass stars are not only in binaries, but are in triples or higher order multiples. In fact, on average, a high-mass star that's the primary of a multiple system has more than two companions. And the most common configuration is a hierarchical triple. So we have now made some progress. We're done with the introduction, and I hope that I've convinced you that it's important to consider mass transfer